So we're going to take a look at this video on physical and chemical properties and changes. Taking a look at physical properties, those are properties of a substance that can be measured without changing the chemical nature of a substance. So something such as boiling point, density, color, shape. There's many more out there. Mass, texture, smell, all of these are physical properties. Physical properties can be broken down even further into intensive and extensive. Intensive are physical properties that are independent of the amount. Notice how both start with an IN. So an intensive property would be something like the boiling point. So regardless of the amount you have, if it's the same chemical substance, it's going to have the exact same boiling point or melting point. Its density will stay the same, as well as its color. Extensive is dependent upon the amount. So if you're taking a look, something that's extensive, something like mass, would be considered an extensive property, or volume. Both would change based on the amount that you have. So thinking about it in terms of the amount is the easiest way to determine it. A chemical property is a property of a substance that cannot be measured without changing the chemical nature of the substance. So something such as flammability is something that if the substance is in fact flammable, you're going to change the chemical nature of it. You can also take a look at corrosiveness. So if you are working with a corrosive substance, you can measure that by if it's reacting with something or if something happens to it. So both of these are a little bit different from physical changes and chemical changes. A physical change is a change that doesn't alter the chemical composition. So if you're looking at it in terms of physical properties, it's those changes. So taking a look, an example of a physical change would be something like a phase change. So if you take ice and you melt into liquid water, that would be an example of a physical change. You can also change the shape or the size of it. You can also dissolve. So if you take sodium chloride or salt and dissolve it in water, you're not changing the physical nature of the substance. It's still there, it's just in a slightly different form. While a chemical change, these changes are the ones that alter the chemical composition. So taking a look at flammability, if something is flammable, it's going to change what the substance is after, if it is indeed flammable. Or if it reacts with something, again, it's going to change it. So these are all different ways of taking a look at physical versus chemical changes. How do we know if a chemical change occurred? There are actually 5 indicators. The first is the change in odor, change in color, energy given off or absorbed, formation of a precipitate, or formation of a gas. So odor, color, those are pretty self-explanatory. So energy given off, usually we can tell this if there's the easiest way for us is if there's a temperature change, but that's not always the case. Sometimes we will see energy in different ways, such as in light. Formation of a precipitate. So a precipitate is a solid substance. So let's pretend for a moment we have this beaker, and there's a precipitate. What it is, it's going to have a solid sitting on the bottom. You can kind of think of it like a snow globe. The snow particulates will all sink to the bottom. And then formation of a gas, so such as some sort of bubbling that occurs. So if you add baking soda and vinegar together, it forms bubbles. Now what we're not talking about when forming a gas is something like boiling. Boiling would be a phase change if you boil water. So that would again be a physical change. So taking a look, just to help identify solids, liquids, and gases, we gave you little particulate diagrams here to help define them. Gas particles, as you can see, there's a lot of space in between, while solids are very organized and very close together. So vapor is different than a gas. Vapors are the gaseous phase of a substance that is normally liquid or solid under standard conditions. And also an alloy is a metallic solid solution composed of two or more elements. So an alloy is often used in various applications. So something like stainless steel is considered an alloy because it's a mixture of various elements to help make it give certain properties that are needed for stainless steel. For phase changes, these would again be physical properties. This little chart helps us to show, I always think of these in terms of water. So a solid to a liquid would be considered melting. Liquid to solid would be evaporation. Gas, or liquid to gas, I'm sorry. Gas to liquid would be condensation. Liquid to solid, this would be solidification, which you might be thinking of in terms of freezing. That would be another way of discussing it. The big overarching ones we're not used to seeing. Solid to gas would be sublimation. If you've ever seen dry ice sublimates. It has this carbon dioxide fog all around it. And then gas to solid would be deposition. So an element is a pure substance made up of only one type of atom and cannot be broken down by physical or chemical means, only by nuclear means. We will talk about nuclear reactions a little bit, but the way that you would find this would be by taking a look on the periodic table. So something like carbon or nitrogen or tin, any element on the periodic table would be considered an element. A compound, this is also a pure substance, but it's a combination of two or more elements that are combined chemically. So if you think of water, so it has two hydrogens and an oxygen, carbon dioxide, glucose. All of these things would be considered compounds. Generally, they're written as chemical formulas, such as I've shown here. Both elements and compounds can be grouped together as a pure substance. Mixtures are a combination of two or more pure substances in which each pure substance retains its physical properties. So we can actually break down, we're going to look at examples of them separately. So we have two types. We have homogeneous mixtures where the combination is uniform throughout. So the big thing is that you can't distinguish the layers here. So something like soda or salt water, these are solutions where you can't tell that they're mixed together. So it's going to be one or uniform throughout. A heterogeneous mixture is where you can identify the individual parts. So a great example of this would be salad dressing or orange juice. Both have different parts that you can see. Now, obviously, there's non-food examples of these. We're just using food examples to make them easy for you to relate to. Heterogeneous mixtures such as muddy water would be another example of something that you might have seen. Taking a look at this chart, this helps to illustrate kind of how matter is broken down. We have matter broken into pure substances and mixtures with a few more examples of all of them here as we described before. You might be thinking, how do I separate these items? So elements, again, can only be broken down by nuclear reactions. Compounds can be broken down by chemical reactions. And mixtures can be broken down by physical means. So we're going to take a look at some separation methods here. So filtration, so you separate by using some sort of porous barrier. So you're separating by particle size. So if you've made coffee, you're using a filter to separate it. Or sand and water, you can separate with a filter. Distillation is going to be separating by the boiling point. So if you have two liquids together, you'll heat them up. If they have different boiling points, what will happen in this apparatus is they will become a gas. They will flow through this condenser, which causes the gas to condense, and it'll come out the other side, separated from the other substance. This is something in a little bit more complicated process that they use to make gasoline and separate all sorts of stuff. Chromatography is another process, and this is based on the attraction to a liquid or a solid. There's paper and column. We usually end up doing paper chromatography. So what happens, so these are kind of illustrate the end product. What you would start with would be a small piece of paper, and you put a dot of some sort of mixture on it. So whether it's dye or food coloring, whatever you want. So then what happens is you put this into some sort of solvent. The solvent wicks its way up, and it will carry up the substance that you put on it and separate it out. So these are examples of food coloring. Food coloring has multiple components in it to make it the color that you see with your eye, but it's attracted differently. So you can see this one right here. We have a green and a pink component. This can be done with all sorts of things. It doesn't have to be just food coloring, and there's other things that you can do with it. But we, on our level, we end up doing food coloring because it's an easy example for us to visualize. And then just in the last thing is the law of conservation of mass, which states that mass can neither be gained nor lost in a chemical reaction. So a chemical reaction is when you have two or more substances reacting to produce a product, or a reactant breaking down into multiple products. There's lots of things, and when we get to a little bit later in the year, we'll talk in more detail about what these chemical reactions look like. Just for right now, we're just referring to the general law of conservation.